Hello. So unfortunately, I realized the first part of the lecture today, the last lesson, the last lecture, is actually not recorded. So let me redo it here again, because here I have a little bit more time and I'm not under stress of time, so I can actually go a little bit slower here and probably make more videos and explain those material a little bit more patiently here. So the first thing we did today was give another example of this theorem, the direct comparison test. Let me just remind you briefly. If I have two infinite series such that an and Bn are ultimately non-negative, if there exists a positive constant k so that all the terms of the sequence of the first series is less than or equal to k times the corresponding term from the second series, then if the larger series converges, then we can conclude that the smaller series also converges. And if the bigger series if the smaller series converges to infinity, then it will actually allow us to conclude that the bigger one also diverges to infinity. Okay? Okay, and then last lesson we actually were able to solve the first part and the second part of this example. Today I want to talk about the last one. So the question is that investigate the convergence behavior of each of the following series and justify your answer. Okay, so here I want to see if this series converges or diverges, and I want to use the direct comparison test as I reminded you in the beginning of this video. And if you remember during the lesson I told you in the class, I told you that if you want to use this direct comparison test, you should have some kind of feeling about in which direction you want to move. If you believe that your series converges, then you have to find an expression that is greater than this one and prove that that greater series converges so that you can conclude that your series, which is the smaller one, also converges. But if you feel that this series is supposed to diverge, then you should change your strategy right from the beginning and try to find another series for which this is greater than that one, but this time that series that you want to choose should be divergent. So you have to have a feeling about that. Okay, so how can I find that feeling here? So one thing is that you see that I have ln of n in the denominator. And if you remember the old lesson, we learned that polynomials dominate over logarithmic functions when n becomes large. So if I ask you which one will win in the competition between ln and n when n becomes bigger and bigger, because n is just a polynomial and ln is a logarithmic function, according to that rule, you will know that n will dominate. So this means that ln of n, you think it should be less than n. And that's good enough, because in that case, then 1 over ln of n becomes greater than 1 over n, and then sigma 1 over n is the most famous divergence series. This is the harmonic series. And then, of course, this is divergent, and this one is bigger than a divergent, then you can immediately conclude that, okay, this series is divergent. So now we get a feeling. And by the way, what I said is completely true, but of course you should do it a little bit rigorously. So, for example, here you see that the smallest value is 2, so I will have a conjecture. I would say that, let us say that if x is greater than or equal to 2, can I prove that ln of x is less than or equal to x or not? So I can, of course, take this off as well. We don't need to put equality sign here. So this is a question. And if I want to prove this, do you remember during the lesson, you define a new function f of x, which is ln of x minus x, whatever you have on this side, and then you move this to the other side. So you construct a function, and your goal is to show that this function is a monotonic function. So for doing that, let me take the derivative. So if I differentiate this function, this becomes 1 over x minus 1. And let me take the common denominator. This becomes x, and in the numerator I will have 1 minus x. And now, because I am interested in this interval, x is greater than or equal to 2, so this means that the denominator is definitely positive, but the numerator is definitely negative. So it means that in total the derivative is negative. So this means that for all x greater than or equal to 2, f prime of x is strictly less than 0. So this means that f is strictly decreasing on 2 up to infinity. Okay, so but what is the meaning of this? If x is greater than or equal to 2, which is because I am interested in that interval, and then I know that f is strictly decreasing, then it means that f of x should be less than or equal to less than, we don't need to put equality, less than f of 2. But if I ask you what f of x is just simply ln of x minus x. And if I ask you what ln of f of 2 is, you just replace x with 2 everywhere, so it becomes ln of 2 minus 2. Then I move x to the other side, so it means ln of x is less than x, but plus a number. That number is ln of 2 minus 2. Okay, but the good news is that this number is a negative number. Ln of 2 is less than 2. Yes, if I ask you ln of which number is 2, ln of e to power 2 is 2 ln of e, which is 2. Okay, and definitely 2 is less than e to power 2. So if I ask you what type of number is this number, that number is definitely negative. Okay, so x plus a negative number is definitely smaller than x itself. So I was able to show that if x is greater than or equal to 2, ln of x is strictly less than x for every x greater than 2. But here I only care about integers. So this means that if n belongs to n and n is greater than or equal to 2, definitely ln of n is less than n, and then, by the way, it's also positive. Okay, because n is greater than 2, so ln of n is also positive. So then it means that I can do the reciprocal. The reciprocal of the first one will become greater this time than the reciprocal of the second one. And then we know that sigma 1 over n goes to 2 to infinity, from 2 to infinity, is divergent, even though this is not harmonic series, because harmonic series starts from 1. But if you remember, we also had a theorem that the behavior of an infinite series does not depend on a finite number of the terms from the beginning of the list. So if this sigma from 1 to infinity, which is the harmonic series, is divergent, this one, which only differs by one first term, is also divergent. And my series here is greater than the harmonic series somehow. So this means that this series also diverges. Okay? Okay, now let us solve this exam question. Determine whether this series is divergent or convergent. And that's an easy task here as well. So for example, let me write 2 plus sine n divided by n squared plus square root of n. Yes? So definitely this is a positive sequence because sine n is minimally minus 1, so the numerator is always positive and the denominator is also always positive. Okay, so the direct comparison test is indeed applicable. Okay, but we have to get a feeling of what type of argument we should follow. So the numerator is more or less I mean, sine n is maximally 1, minimally minus 1, so the expression in the numerator is between 1 and 3. Okay, so that's a number oscillating between these two. And then if I ask you what is the dominant term in the denominator, because n squared has a bigger exponent, so this means this dominates. So this will be a constant which oscillates in the numerator and n squared in the denominator. So roughly speaking, it is comparable with a p-series in which p is 2 and greater than 1 and it is convergent. So we get the feeling that this sequence should be also convergent. Okay, so then it means that I should make it, I should bring another expression here so that this one is less than that one and somehow this is convergent. Okay, but that's very easy because, for example, I can say that the numerator is less than 3 divided by n squared plus a square root of n. Why is that? Because these two fractions have the same denominator, but the numerator of the first one is at most 3 because at most sine n is equal to 1. So that's what I have written is correct. But then I can go and say that, okay, this is also less than or equal to 3 over n squared itself. Okay? And then this series is a 2 series up to a constant factor 3. So this means that this series, sigma, 1 over n squared, n goes from 1 to infinity, converges. Why? Because it is a 2 series and 2 is greater than 1. So then we can conclude that, okay, if I multiply all the terms by 3, this also converges. And I was able to show that the sequence for my series, all of them are less than or equal to the terms of this convergent series. So according to the direct comparison test, this series also converges. Okay, so let me give you one point here. So I want you to understand, because some of you might say that, okay, how should I know to keep n squared? Because you know, in principle, I can say that this is also less than or equal to 3 square root of n. That is not wrong, but useless. Why is that? Because if I write this inequality, that is not wrong, but the problem is that this is a p-series with p equals to 1/2. Why? Because a square root of n can be written as this one, and then because p is less than 1, this diverges. So this inequality on its own is correct, but it doesn't take me anywhere because this is divergent. And if my sequence is less than a divergent one, there is nothing I can conclude about my own series. So that's why this inequality is true, but it is useless. And this is more or less the only way we can solve this problem. Okay, so now let us do the next one, which is also an exam question. Show that for every integer n greater than or equal to 1, this integral from cosine of 1 over n to 1 of 1 over t dt is less than this number. And then for the second part, we're supposed to show that this series actually converges. Okay, so let us concentrate on doing this one first. Okay, so what we do here, we can actually start calculating this integral. For example, if this was given to me in an exam question, the first natural thing for me comes to mind is to calculate this integral and show that this number is less than this number. Why? Because this integral is not hard to calculate. 1 over 3 is a very simple integrand. I'm not saying that you will see that this is not indeed the solution for the first part, but it is useful, as you will see. So for example, what I do, let me change my color to green. So in principle, this is a scratch paper work. So I would say that integral from cosine of 1 over n to 1 over t dt, this is simple to do because a primitive function for 1 over t is ln of absolute value of t. I have to run it from cosine of 1 over n to 1. So then I replace t with 1. and then I replace t with cosine 1 over n, but absolute value of 1 is 1 and ln of 1 is 0, minus the second one does not need any absolute value because n is an integer greater than or equal to 1, so 1 over n is positive and it is less than 1 or less than or equal to 1, and this is also less than pi over 2. So this means that 1 over n is an angle in the first quadrant. And in the first quadrant, cosine is positive, no matter what n is. So I don't need any absolute value, so this becomes ln of cosine of 1 over n. So this can be simply written as minus ln of cosine 1 over n. Okay, so you see that if I want, so in principle, this integral is this, and I have to convince myself that this is indeed smaller than that one. Of course, if you can somehow do that, it's no problem, but it is not a trivial inequality. On the one hand, I have a logarithmic and trigonometric functions involved, and on the right hand side, I have a little bit complicated form of a trigonometric function. So I would say that this is the most natural starting point, but it is not working. But as you see immediately, it is not useless, because now you see that this integral appears in front of this sigma in the second part. So let us keep it and try to change our strategy. So direct calculation apparently does not work. So this means that I have to use the properties of definite integrals for inequalities. Okay, so what I can do? I can say that now this is the solution. So let me write part 1. I would say that in this integral, I am working on this interval from cosine of 1 over n to 1. Okay, so this means that t is somewhere between cosine of 1 over n for a fixed n up to 1. So this means that 1 over t is definitely greater than 1. Yes, because if t itself is less than 1, its reciprocal becomes greater than 1 and becomes less than or equal to 1 over cosine of 1 over n. So what I'm doing is this. If I have 0 less than a, less than b, less than c, then if you want, you can conclude that 1 over c is less than or equal to, is less than 1 over b, is less than 1 over a. And of course, if I have equality signs here, these will have equality signs as well. So I'm using this. Okay, but now we don't need this part. We concentrate on these two. I have a function, 1 over t, which is less than another function. Of course, this function is a constant function. If that is the case, the integral of this on an interval will be less than or equal to the integral of this function on the same interval. So it means that the integral, so let me change my color, so the integral of 1 over t dt from cosine of 1 over n to 1 is less than or equal to the integral of the second function, cosine 1 over n, 1 over cosine 1 over n dt cosine 1 over n to 1. But this one is easy to calculate now because this is just simply a constant. The variable of integration is t. So this becomes 1 over cosine 1 over n, and then I have integral cosine of 1 over n to 1 dt, but integral of dt is just t, so this becomes 1 over cosine of 1 over n, and then 1 minus cosine 1 over n, yes? So the integral of dt becomes t, and I have to run it from cosine of 1 over n to 1, so this becomes this. So what I was able to show, that this integral, which is this one, is less than or equal to this expression. But I were not supposed to show that this integral is less than this one. I was supposed to show that this integral is less than this expression. Okay, so I have to manipulate, hopefully, this expression algebraically so that I can get as close as possible to the expression given in the question of the exam. The first thing is that you see that I need sine squared of 1 over n. For having sine squared of 1 over n, I'm hoping that I can put a 2 here, because if I can put a 2 here, then it becomes exactly what I need. But of course the problem is that the 2 is not there. Okay, but that is now simple. If you understand this, it is not hard. So I copy and paste this one. So let me write it in this form. 1 minus cosine of 1 over n divided by cosine of 1 over n. And then I multiply it by 1 plus cosine 1 over n, but I'm not allowed to change the problem unless I compensate for the change, yes? So what I have done, I have rewritten this expression in this form, and that's completely valid because this is nothing except 1. But what is the benefit? The benefit is that if I multiply these two, that's the conjugate rule, so it becomes the first one squared minus the second one squared, and then divided by cosine of 1 over n times 1 plus cosine 1 over n. The numerator becomes exactly as I want. So 1 minus cosine squared is sine squared of that expression, so that's very good. But the problem is now that I have a little bit problem in the denominator, because the denominator in the problem is a little bit simpler. It's just simply cosine squared of 1. Okay. They cannot be equal, of course. This is clear that this expression is not equal to the denominator of this one, but be careful. I don't want equality. I want to make sure that this one is less than or equal to the one given in the problem. So I will make it like this. I copy and paste the numerator because I need it. That's exactly the expression given in the problem, but hopefully you agree with me that if I write this one. Okay, so let me explain. So you see the numerators are the same. These parts of the denominators are the same. What I am telling you is that 1 plus cosine 1 over n is greater than cosine of 1 over n, which is clear. Yes, because it has an extra 1 in it. So this means that the numerators are the same, but the denominator of the first one is larger than the denominator of the second one. So this means that the fraction as a whole is less than this fraction. Okay? But that is also not completely what we want. So I copy and paste this one. And then I would say that I can write it as cosine squared 1 over n. Okay? But now this one itself is less than or equal. I copy and paste the numerator, but instead of denominator, I simply put cosine squared 1 in radians. Okay, why is that? I am claiming that this expression is greater than that one, so that the whole fraction is smaller than this fraction. And that is obvious. Why? Because 1 over n is less than or equal to 1. Because n is a natural number. If I put n equals to 1, then 1 is equal to 1. But if I increase n, 1 over n is definitely smaller than 1. So 1 over n is definitely less than or equal to 1, and of course I know this is positive. So this 1 over n, and because 1 is less than pi over 2, 1 over n is definitely in the first quadrant. Okay? And then what happens, cosine of 1 over n is definitely less than cosine of 1. Because when I make the angle smaller, this will get closer to the x-axis. Okay, so when I make the n bigger, the angle becomes smaller, and when the angle becomes smaller, cosine becomes bigger. So cosine squared of 1 over n is definitely less than cosine squared of 1. So I was able to do that. So if you now combine this, you see this expression is less than this expression, and I was able to show that sometimes they are equal, but sometimes this is less than or equal to this expression. So we were able to, hopefully you agree with me, we were able to show that this expression is less than or equal to this expression. Okay, so that is the first part of the problem. Okay, so now let me move what I need to the next page. Okay, so this is what we have. Yes, we were able to show that this is correct, and accidentally we also discovered that on the other hand this integral can be calculated exactly, and it is equal to this expression, okay, which appears here. Okay, so in other words, it means that this expression, which is the answer to this integral, is less than or equal to this expression. So yes, so this means that ln minus ln of cosine of 1 over n is less than or equal to sine squared of 1 over n divided by cosine squared of 1. Okay, and by the way, this is also positive. Why? Because 1 over n is in the first quadrant, so cosine is positive, but we know that cosine is less than 1, and the ln of a number less than 1 is negative, so this negative will make it positive. So that's correct. So this means that the sequence that sits in front of this sigma, using the first part of the problem and this calculation, which is now part of the solution to part B, so you have to include it for part B, is less than or equal to this. Okay, so now what I want to do, instead of looking at this sigma, I want to look at this sigma, okay, sigma of this expression. So sigma sine squared of 1 over n divided by cosine squared 1, n goes from 1 to infinity. Okay, because this inequality is in smaller than or equal to, if I am lucky and I can prove that this series converges, then the smaller series also using the direct comparison test converges as well. But that's also simple. First of all, this is a fixed number, so you don't need to be worried about this constant. So you can reduce this problem and ask yourself, is this convergent or not? Okay, and that's also simple. So if you remember, we had this famous inequality that if x is positive, sine x is definitely less than x. This is a very famous inequality. So this means that sine of 1 over n, 1 over n is positive, is definitely less than 1 over n itself. And I raise it to power 2, so sine squared 1 over n is less than 1 over n squared. And we know that sigma of 1 over n squared is a p-series in which p is 2, so it is convergent. Yes. So in principle, this means that this series is convergent because its terms are correspondingly less than the terms of a p-series with p greater than 1. So the convergence of this will imply the convergence of this, and the convergence of this one implies the convergence of this one because they just differ by a multiplicative constant, and convergence of this one according to this relation, which we'll learn this true from part 1, guarantees the convergence of this sequence. But what you need to do in the exam, you have to write these properly. Okay, so I will stop this video here now, even though in the lesson we continued, but I will make another video and then upload it for you. Okay, thank you very much. Until the next video, be safe and goodbye. Thank you.